Hey everyone, welcome to my talk, which is about scalable global illumination for O3DE. I am pretty excited to be here. It's my first time ever at O3DCon. But seriously though, it's great to be part of such a new and exciting endeavor in gaming. My name is Tobe and I'm the principal game engine architect at Huawei. And the reason I want to give this talk today is that in the past I've experimented with quite a few global illumination implementations, particularly volume-based, and I want to discuss how to make a great GI system for O3D that avoids many of the pitfalls one can run into, particularly with pro-based systems. Before we get started, let me quickly paraphrase what this talk is about. O3D is fresh out of the oven, and one of the key ingredients to make a game look realistic and beautiful is global illumination. Now, before you all get excited that I've somehow implemented the latest SIGGRAPH craze in my spare time and pushed a PR, I want to assure you that I did not. What I'm going to do today is to try to establish how we can make a global illumination system inside O3D into something that is artist-friendly and fun to use, something that scales across game genres and the device spectrum that we have today, and maybe something more, and how to design a system that is future-proof, that is, rather than falling apart and be replaced, it can be expanded upon. I want to stress that this is not a complete solution, rather than a series of questions what issues we actually want to solve by looking at O3D and what O3D currently has for GI and determining whether for general purpose engine we need to expand on it. Having said that, you may be scratching your head now and will ask, well, Tobe, what is this global illumination in the first place? So there are a couple of ways to present global illumination, for instance with the path-space integral or the more classic rendering equation. But personally, I prefer to use images. So every 3D scene starts with not just geometry, but with a bunch of lights. In this scene, for instance, we have a rectangular light source on what appears to be some kind of ceiling. And if we'd stop right here, that's all we would ever see, an empty void and something bright shining in the middle of nowhere. Once light hits a surface, that light can be reflected into the camera and the viewer's eye, and this is the first bounce of light, which is sometimes called direct light. Now, direct light is relatively easy to compute, except for shadowing effects and the fact that most engines pretend light sources are infinitely small points. We only need to know a position on a surface, its material properties, the position of all light sources, and the energy carried across that space. However, if you've ever set up your living room, you know that there are two ways to deal with light sources. You can either make them shine directly into the room, or you can point them at the wall and have a somewhat softer, more ambient light that bounces off the wall. And so we arrive at the second bounce, where light bounced off a surface onto another one and then made its way into the camera. So here you can see the red tint on the Lucy statue coming from the red wall on the side, a green tint on the right side of the cube, and some reflections from the mirroring surface down below. Because we only have at maximum 2 bounces right now, the red tint visible on the side of the Lucy statue is not actually visible in the mirroring surface below, because that would require 3 bounces. And so, of course, we can repeat this bouncing light effect over and over. But then again, with each new iteration, the contribution is smaller and smaller. So eventually, we could argue that the result is just good enough. Of course, this process is complex, hard to compute, and full of issues dealing with the types of materials that light can interact with. For instance, we saw that our metallic surface that we had in the previous image, the effect there seems to be visually much stronger than for other surfaces. Games mostly simulate diffuse global illumination, the type of lighting that you get when it bounces off diffuse surfaces. And the good thing about diffuse light is that it is view independent and can therefore be pre-computed, independent of the viewing angle. So over the years, there have been many proposals how to deal with global illumination, how to compute and store it, and how to sample it at runtime. I'm now going to list several different methods divided into 3 rough categories, which describe how they commonly store and sample global illumination. First, we have surface-based methods. Here the idea is to store contribution of global illumination directly at the surface level. Shadowing and bounces are put into vertices, textures, or other surface representations. These surface representations usually are easy to sample, and we can store global illumination for each object independently. It doesn't even have to be a full result. We might also store some helper information, such as in pre-computed radiance transfer methods, where we use this information later to calculate the final result, and instead of being completely fixed, we can change the lights at runtime if the surfaces stay fixed. So the classic one in this category are light maps, where we essentially spray paint GI into texture maps. Then we have the surface-based methods, where we chop up space into small surface elements, for instance, dots or small circular areas, and use those to compute GI. Commonly known algorithm here is irradiance caching or virtual point lights. A subclass of these algorithms is pre-computed radiance transfer, which strictly speaking isn't tied to surfaces, but that's where most implementations have been made so far. Where we also store texture maps, but those contain a partial solution of the rendering equation using a clever trick to evaluate the integral in frequency space through a dot product later, allowing you to change the lighting of the scene as long as the geometry remains rigid. So the good thing about surface-based light transfer is that all of these methods tend to be cheap when sampling. That is, runtime light mapping is just texture mapping. Volumetric methods are different. Here, global illumination is stored in space, meaning we store the light passing through a sample of space. The good thing about these methods is that they can be sampled by dynamic objects that are moving through space. That is, they can pick up light as they go from nearby samples. Another great benefit is that since the information is stored in a volumetric fashion, it can be combined with other volumetric effects, such as smoke, where indirect light interacts with particles in the air. It is also easier to author than surface-based methods, as we do not need to worry about how to distribute global illumination along complex surfaces. For instance, with light maps, we have the same problem as with other texture maps, where a rectangle, for instance, doesn't fit very well across a sphere. Famous representatives in this category are sparse voxel octrees, where GI is stored in a voxel hierarchy of varying voxel sizes and is sampled using cone tracing. This allows us to gather not just diffuse GI, but also compute specular indirect bounces. Irradiance volumes, another classic, which are regular grids of light probes, such as in the image below, sample light and usually store the result in smooth spherical harmonic representations, which can be interpolated nicely. Another new contender, as seen in a recent Godot implementation, is SDF-GI, where geometry is resampled into signed distance fields, which can speed up ray tracing dramatically. Again, a major improvement of this category over the previous one is that one no longer has to worry about geometric complexity and that dynamic objects can sample GI too. The last category are screen space methods. Here we capture and store global illumination directly from the point of the viewer. The amount of work that is done is fairly predictable, as it basically is tied to the screen resolution, and we can therefore use, for instance, upscaling methods to reduce the amount of rays we need to compute. Screen space GI performs ray tracing directly on the available G buffer in a post-processing pipeline. These methods suffer from the same issues that all G buffer-based post-processors do, which is that they fail at screen edges when the rays need to leave the G buffer sample area. The good thing is that these methods can be augmented by ray tracing to fill the gaps and get much cheaper results than ray tracing the entire image. I've also included analytical light sources here, which are usually used for large emissive surfaces, even though this only covers part of a specific type of GI. Screen space methods are great because they require the least amount of setup. They are not tied to geometric complexity, and they do not require us to choose a sampling density in space. But it turns out that, surprisingly, all of these categories have some sort of issue. First up is all of them require some choice about the density of the collected samples. So for surface-based methods, it's the texels per unit of map geometry. For volumes, it is the amount of subdivision of a unit of space. And for screen space methods, it is the resolution of the camera. And all of these show aliasing artifacts that can have wildly different looks than those in the previous category. Unlike surface-based methods, subdividing space in 3D means we end up with samples inside geometry. Screen space resolution, on the other hand, can directly influence the detail that is dependent on just the camera angle. More importantly, though, surface-based methods usually require careful UV editing and workarounds for LOD geometries, as one usually cannot reuse light maps from one level of detail to another one. So sampling, however, is pretty cheap, as I mentioned before. Volumes suffer from different artifacts. Sample positions in space may be stuck inside geometry, or the density is slightly too low and two probes on either side of a wall are interpolated and leak through it, or they can miss important changes in lighting entirely. Volumes with regular sample positions also force alignment across a section of space. So non-volume aligned objects like, for instance, rotated houses will end up with terrible aliasing and wobbly GI across their surfaces, and they also tend to be quite memory hungry. SDF GI offers a way out, but requires pre-computed signed distance fields to really improve ray tracing at runtime. There are some great things about volumes as well. They can be combined with other volume effects, and dynamic objects with no GI can sample them just like static objects. Screen space methods seemingly come to the rescue as they have none of these issues, but they are either limited to a G buffer, so shallowed angles and off-screen geometries aren't handled, several layered or depth field buffers, or simply require expensive ray tracing with pretty hard choices between bias or noise. So how should we evaluate GI methods for O3DE? Going back to my intro slide, I want to define the three categories I have set up. What do I mean by artist-friendly, scalable, and future-proof? Well, clearly, a robust GI solution for O3DE is one that can be set up quickly and be refined easily, and that would be preferable to a GI solution that needs a lot of fine-tuning and adjustments. Ideally, an artist working on any type of scene, even a huge one, should have no problem setting it up in a matter of minutes and at least be satisfied with most of it, save some details. The chosen GI solution should also allow for quick iteration, meaning if some lighting setup has been changed, we can see the results quickly. Because nothing is as frustrating as changing one little detail and then having to wait another hour for a result just to find out that this was the wrong change. Something I've taken from a recent HPG talk from Alex Evans is that the solution that one can work with nicely is one that has hard predictable limits, that is easy to fix up within those limits and hard to break. That is, a good solution is a robust one. Finally, the chosen GI solution should allow us to support a multi-artist workflow, where in a future scenario, many artists can work on the same scene in parallel and potentially even make use of each other's computation running in the background. When it comes to scalability, this can also mean a few different things. On one hand, a scalable solution is one that can be easily adjusted toward a target platform. Ideally, an artist could tweak some parameters to make a GI solution run on a different target platform without having to re-author the entire lighting setup of the scene. The type of hardware and the algorithm that we're using can be a good fit or a bad one, and ideally we want to make use of as many hardware resources as we can. Another crucial aspect is that in many games we see customized GI solutions for a specific genre of game. For instance, open world games and dungeon crawlers or indoor shooters rarely make use of the same methods, but ideally an artist doesn't need to understand why, because we found a good solution for everything. Included in that solution is some kind of multi-scale support for GI that allows us to up or downscale the quality of the GI solution based on distance, per pixel ratio, or memory consumption. Finally, a solution that can be chunked up into packages and distributed to multiple GPUs or even other machines in the same network would allow artists to distribute baking or real-time computation of massive, high-quality GI, and that requires a somewhat defined streaming behavior. I called the final category future-proofing because graphics is a fast-paced field, and we ideally want our GI solution to survive for a couple of years. In that sense, I think a flexible approach that allows baking, real-time GI, or even something in between would be ideal to handle different scenarios and target platforms. Ray tracing is on everyone's lips, but not yet everyone's phones. So having a fallback to baked only is a good thing to have, even only for optimization purposes. O3DE is a gaming engine first, but just like other game engines, over time it will attract different users. Architects, AR developers, medical and automobile visualizations, and of course, movies. All of these fields have very different use cases for GI, and ideally O3DE can cater to these needs with solutions that we come up with. O3DE's gem system allows for the engine to be highly extensible, so I'd wager we'll see custom GI implementations and all kinds of other effects added to the Atom renderer soonish. Ideally, the native chosen GI solution can work with these new effects well together, meaning one can, for instance, control for the different types of GI in different parts of the scene, or combine GI with effects such as volumetric fog. Finally, distributing GI work packages can be extended to the cloud, just as I'm able to extend my compute capabilities by requesting an additional compiler daemon from another computer, or maybe run my AI training with an additional compute resource from other machines. I, as the future player, would really love and like to rent an additional GPU if need be. Diffuse GI for such a service is a great target because it's low frequency, changes slowly, and so it compresses nicely and allows for some lag before displaying. However, in the long run, we should investigate a way to support more than just diffuse GI. So this is how the GI implementation looks to the user right now in O3DE. We place a box and attach a diffuse probe grid component, which will fill it with probes. The implementation is based on DDGI, a regular grid based on octahedral encoded probes, which uses GPU-based ray tracing to update those at runtime. Because ray tracing probes is expensive, grids go with a lower density of probes and compensate for leaking issues by encoding interprobe occlusions sampled together with the GI. Additionally, there are the usual biasing parameters to avoid self-lighting and fetching the wrong GI when surfaces, for instance, are too close to probes or stuck inside geometry. In O3DE, grids can be placed with boxes into a scene with specified probe density. Those can be either baked, in which case at runtime only resampling the grid is required, or they can be real-time, in which case ray tracing will update the probes at runtime. What's real nice here, especially for iteration, is that there are two separate modes for the editor and runtime, so a beefy editor can be used to get updates live and still bake the results for production. Probe grids are independent from one another. They're culled, and each probe grid uses a pass to add its portion of GI to the rest of the image. If the grids overlap, the highest density one wins. Culled volumes stop updating if they are set to real time. There's currently no blending when leaving the grid. That is, any GI will be cut off immediately at the edge. So I want to come back to the three categories that I've mentioned earlier and ask, is the current implementation artist-friendly, scalable, and future-proof? Right now, authoring seems a bit painful, to be honest. The usually quite low resolution of the probes is needed to avoid high sampling costs and waste probes at the same time. But that, of course, introduces leaking everywhere, and the occlusion buffers won't fix all of the issues. Additionally, the regular layout of the probe grids causes really bad aliasing artifacts along rotated objects inside a grid, with many probes getting stuck inside geometry. Basically, the artist needs to balance scaling costs and visual quality by hand. Grid overlaps currently pick up the smallest volume for rendering, but ideally we'd like to control for the highest density or even combine different BakeGI results. When authoring large scenes, the artist is forced to either place loads of boxes with varying densities to sort most of the aliasing issues, or for real-time mode, attach a grid to the camera and have a cascade move around with the player, but with a fixed density, which will show artifacts very quickly when moving past thin objects and probes get stuck in geometry again. Scalability-wise, for bake probes, we need to split grids and scatter them around in scenes, which increases the amount of draw calls to render once we have a big bunch on screen. Additionally, there's no level of detail support, so we could easily end up with an open world scenario with 1K probes covering a single pixel on screen. And right now, as far as I know at least, there's also no way to prioritize the streaming order of grids, like important grids. So that would be those that cover large areas or those that are close to the player. Baking large scenes doesn't matter in real-time mode, but for bake probes there's no explicit parallel baking support when using multiple grids. Ideally, those would bake in a progressive manner, starting with the grids in the editor view first and then expanding around the camera. Also, bakes cannot be distributed to other machines in a network right now. So when we think about possible future usage scenarios of O3DE, there are also some currently undefined targets. The occlusion buffer in DDGI could be reused, but we have no definition in place how to combine other effects in the graphics pipeline with or even new GI implementations with DDGI right now. A common feature for open world games are light treatments, so rebakes of the same scene with different lighting conditions that are blendable. But right now we can pre-bake several texture sets and only flip them. Another cool feature that is currently undefined is something that we see in other engines, namely creating alternate representations of geometry for fast occlusion tests, for instance. Having signed distance fields ready for every piece of geometry could be really helpful in a lot of scenarios, even next to GI. Beyond diffuse GI, there's currently no plan. We have reflection probes, but as far as I'm aware, we are currently missing screen space reflections with ray tracing support to fill the gaps. And then we think about verticals such as movies. Lighting artists in these areas are used to much higher quality levels. So here we hit the limits of DDGI rather quickly. I have a proposal for the first enhancement to O3DE. So assume this scene is the scene that we have on the screen, and we've drawn a diffuse probe grid box in blue around it. We can split up the scene into equal chunks of n-cube probes wherever there's geometry or an emissive light source or a navigation path or something else that serves as a heuristic to find interesting changes in lighting. Since probes capture radiance or irradiance, we would ideally subdivide leaves and place them at positions where we expect drastic lighting changes. But that puts us in a bit of a chicken and egg situation where we now have to compute the GI before we know where to put the positions where we want to compute GI. In its place, we have a lot of good heuristics though. We know that lighting is more interesting around geometry and even more so around complex geometry. Additionally, good probe coverage is more important along navigation paths and around certain objects such as emissive surfaces. With adaptive placement, we can refine the positions of probes to a degree where they do not get stuck in geometry and stick close to it, so we can avoid leaking through thin objects or from the inside of geometries. This distribution won't be perfect, but it will take care of, let's say, 90% of the work. If the geometry, emissive or navigation path in a leaf of a grid is too detailed, we continue the subdivision. In each leaf, we now distribute probe positions. And notice how the pink probes overlap with the more fine-grained leaves on the right. This is so that we do not need to fetch neighboring blocks for probe interpolation in shared spaces. The leaves or chunks provide a natural way of loading and streaming in higher detail levels for probes later. We can easily map this representation to a tightly packed array with an indexing scheme which would later allow us to request specific leaf nodes in the subdivision scheme. So what do we gain? Artists now specify a maximum probe density, that is the amount of probes per square unit of space, and simply slap one giant probe grid across the scene if they want to, and the automatic subdivision should take care of the setup. Because of the adaptiveness, we get better representation for our captured GI and avoid leaking issues much more nicely. This setup will go a long way, but of course it won't address all problems. Which means we'll need some tools to fix those places where the heuristic simply failed. Again, the core idea of using an adaptive structure is to capture changes in lighting, and we can't know where that is unless we first compute it. So for the last 5% of issues, we need to use the artists as our probability density function. There may be, for instance, places in empty areas where drastic changes in light are due to indirect light, so something that is not actually captured by any of our heuristics. This happens, for instance, quite often when changing from outside areas with a bright daylight to an inside area, like a cave, where the bounce reflection in the entrance area dominates the light in the cave. In this case, a tool like an additional box would allow the artist to force extra adaptiveness on an empty area that would otherwise stay with a low density. Other tools would allow to specify offsets for probes to move them from problematic areas or to suppress their contribution altogether. By using adaptive grids, we are not just freeing artists from work to automatically place probes in areas that matter, but more importantly, we save probes where they don't. Another approach is the one taken by Activision, which is to compress entire grids with a moving basis function. With adaptive grids, though, we not only get a representation of valid change in lighting, but also an effective level of detail mechanism baked into the structure. Splitting up the grid into equal-sized chunks also allows us for predictable distribution and gives us additional culling options. So grids can now be easily computed in part, and chunks can be shared between editor instances. With proper level of detail mechanisms for GI, we can also provide a first type of scale that allows artists to up or downscale the amount of probes that they need for a target platform. Finally, I want to highlight some important developments for the future. Diffuse GI, once a streaming and sharing architecture is in place, can be requested as a service where one could rent additional virtual GPUs to get any baking task done more quickly. There are also a few opportunities when it comes to the sampling code itself. Diffuse GI can be used in post-processes like volumetric fog and screen space GI. Volumetrics add a great depth and ambience to the scene. And by combining those with GI, all those small emissive surfaces really start to shine and glow. In the animation below, I've experimented with fading bake GI in and out that is also sampled by volumetric fog. But let's not stop there. There are a lot of opportunities to think of GI in terms of layering effects, just like in a popular image editing software. So in O3DE, right now we can overlap grids. And for instance, on the right, you can see a probe grid computed for the little house and another probe grid computed for just the ceiling with different outcomes. Overlapping probe grids could define blending operators to fuse one set of probes with another and achieve semi-real-time effects with baked probes. Speaking of blending, we should also start this discussion around pre-baked light treatments and day-night cycles. So the typical workflow is to set up lighting in a group and then switch it out for a different group and rebake the scene. Adding a drop-down list to store where an artist could add a new named bake to the grid and then have a simple API to fade from one bake to another one would be one way to do it. Movie productions usually require much higher fidelity than games, so with an adaptive structure and no hard texture size limits, we can support much higher probe counts. However, just like this year's Nanite is a way to free artists from geometric limitations, I'd like us to think about how we can free artists from probe count limitations. Finally, there is a lot of potential to improve not just GI, but other systems such as physics by thinking about alternative geometry representations. There are some engines which generate signed distance fields automatically on import, and the asset processor could be enhanced to create sets of representations for imported geometries and materials that speed up GI computation. So here are a set of references for related work, as the topic of scalable probe-based illumination is quite big and there are quite a few variants out there. However, I'd like to highlight the extensive work from Activision on probe-based rendering, even though their solution is a bit specific to the Call of Duty series and those types of games, and a 2013 paper from NVIDIA on cloud-based GI computation. Given that we're now at a turning point where we have high throughput and low latency network coverage, this paper is really interesting for today and even more so for the future. And with that, I'm at the end of my talk. Thank you all. I hope I can stir up a lively debate about GI in the SIG Graphics audio channel to discuss and drive the development of a system that is easy to use, that serves all of our projects, and that we can rely on in the future. And before I forget the obvious, we're hiring. If all this sounds great to you and you're passionate about shaping the future of game development and you really enjoy research and development on a big open source project, look no further and drop me a mail. I'd really like to hear from you. Cheers.